One second, Matt.
Oh.
Wait, just wait for the live stream.
Oh, sure. 4, 3.
Pete's good to go.
All right. Welcome to a special department seminar given by Dan Fortier. This will be part of his master's thesis. It's a public presentation. And he came to our department about 2 years ago. And I must say I've really enjoyed working with him, both as a RA and as a TA in 171. I guess for how he became interested in meteorology, I think it was in the second grade where perhaps his instructor, the teacher in Massachusetts, thought, I'll stimulate STEM education by keeping the window wide open during a horrible thunderstorm. And there was this loud crash, and I guess it made a big impression on him. And so that's a pretty good origin story, lightning bolt in the second grade. Mine's not, it's a little more humble. Third grade, golden guide to a weather gift, like a little kid looking at, what's this doldrum symbol? I still can't figure it out. But we'll keep that idea in mind. Will this manifest? So he then, time went by, and he went to St. Michael's College in Vermont, and he obtained his degrees, 2 degrees in data science and mathematics, but he also acquired expertise in statistics, which has proven to be very beneficial for this study. I've enjoyed learning some statistics from Dan, actually. Interesting techniques that he'll show you. But then I think in his junior year, he took a meteorology course, and Jerry said it struck him like a thunderbolt. Well, no, he decided to go into meteorology and apply it here. He also has a strong interest in athletics. He was hoping to do something in athletics, but that one course, I guess, changed his mind. He was on the NCAA team for swimming at that college and was the captain of the team for 2 years. And he's continued in his love of that with advising and coaching kids from 6 years old to high school, still here in Madison. So I shouldn't take up too much more time. Here's his presentation, investigating the cyclic nature of potential vorticity in Gulf Coast tropical cyclones.
All right, thank you, Matt. All right, so as Professor Hitchman said, my name is Dan Fortier, and today we are going to be focusing on the diurnal cycle of potential vorticity, and we're going to have kind of a focal region in Gulf Coast tropical cyclones. So all of the work that's been done here has been mainly focused in the Gulf of Mexico, the land that surrounds it, the Gulf Coast, Cuba, Central America, all of that. Our goals for this research is to better understand how the ECMWF model is forecasting the dynamics of hurricanes and convection by using potential vorticity, and we'll introduce an index that uses potential vorticity later in this talk. For the future, kind of what we're hoping this kind of amounts to is benefiting forecast of hurricanes, future forecasts, and also possibly ties to rapid intensification, which has more so been looked at in both Professor Hitchman and Shelley Rowe's work so far with tropical cyclones outside of the United States. And so for this project, I've worked very close with Matt and Shelley, who have helped me tremendously in understanding both the science behind this project in particular, but also in the field in general. As Matt alluded to, I did not have a strong weather background when I came here. I was very statistics focused, and so came here, didn't know what way a low pressure system rotated and all of that. So I'm very happy to be up here and presenting and be able to actually understand science now. It's great. All right, so where are we going to kind of head over the next 45 or so minutes? Hopefully I don't go too long. The first part of this presentation is going to be looking at the 2020 Atlantic hurricane season. So overall, it was a record-breaking year. There were 14 hurricanes during the 2020 season. 7 of those were classified as a major hurricane, and many of them went through the Gulf of Mexico. And that's why this became our main focus of the research for this project, was just the repetitiveness of having tropical cyclone after tropical cyclone going through the Gulf. And we wanted to kind of just look through that and see kind of the effects and see if there was any way to forecast this through model data. So after that, the next part is going to go over a brief introduction to prior diurnal cycle work in tropical convection. So we're not kind of narrowing it down just to tropical cyclones, but convection as a whole. And that's just because a lot of research has been focused more broadly and not as succinct. And so in the different papers that we'll go over, there's been multiple variables that have been looked at, one being brightness, temperature, precipitation, convection. Then we have a PV variability index, which is partly what my work is, but also what Shelley and Matt have created throughout their time working on this. And then also the ways of collecting data are very broad in terms of each of these papers. So they're not just focused on model data. We have observations, satellite data, and models that are being used in this section of past work. After that, we will look at the data sets and methods, and I'll go over our research questions, which we'll be looking at in this presentation. Here I'll explain the ECMWF data, which is used for our work, and we are also going to go behind the reasoning of using potential vorticity, and especially the upper troposphere and lower stratosphere. Then we'll start to transition into the research that I've done on this project, and we're going to start with a case study of Hurricane Marco. The reason for using Hurricane Marco was it actually is the first storm that I looked at when I came here, and also has kind of been the test dummy for all of my work. So whenever I come up with a new statistical approach or a new plotting method, that's always the one that I revert back to because I just know it the best. But also it exhibits a really good diurnal cycle that is kind of fun to look at overall. It was a short-lived Category 1 hurricane, and that leads to why we're going to also go into a composite analysis. And we'll actually look at two different composites. One is going to be a little bit more brief, which focuses just on the 2020 season, so that was the start of our research. But then to add a little bit more data in and to make it a little bit better statistical statements, but statements and conclusions overall, I added 2 extra years, 2021 and 2022, just to get a little bit more data going into each of our bins and create better statistical statements. And then lastly, we'll end with some conclusions and future work for our research group as a whole. So with that, let's kick it off with looking into the 2020 Atlantic hurricane season and the devastating effects that it had on kind of just your average Joe overall. So it was a doozy overall, and the first way that we can see that is just looking at past article headlines that were out during the 2020 season, just put out by different random newspapers that focused, number one, on deadly flooding in North Carolina, historic disaster from Hurricane Laura, Alabama having disasters and flooding and just hit hard by Hurricane Zeta, the death toll in Louisiana rising to over 25 from Hurricane Laura, 2 major hurricanes that ended up hitting Central America in 2 different weeks, 2 straight weeks. And then Hurricane Delta also having a pretty high death toll for storms recently. And then I just wanted to end this with the overall summation from NOAA. This is at the end of the 2020 season. After Iota ended up hitting in November, they said record-breaking Atlantic hurricane season draws to an end. And so the records that it broke, where I already alluded to this, hurricanes with 14 and major hurricanes with 7. And then also, this isn't a record, but just to kind of put into perspective how damaging it was, the Department of Insurance said that there were $40 billion in damage from just this one hurricane season tied to each of the storms. So, kind of going into a background. The season had an early start with Tropical Storm Arthur nearing the East Coast in May. And actually in May and June, we can see that there were actually 2 storms in each of those months. That's pretty early for a hurricane season in particular. The first major hurricane is here in August, and that's Hurricane Laura, which hit in the end of August. September was especially active. There are 9 different tropical storms listed. However, I think October ends up being the most active in terms of just potential. There were 4 major hurricanes. 3 of those actually went through the Gulf of Mexico within 1 month, so that's crazy overall. And then our last major hurricane actually ended up ending the season in November, and that was Hurricane Iota, which ended up making landfall in Mexico overall. So here's just a quote that I think kind of sums up just the devastation. So in 2020 alone, there were 7 different billion-dollar tropical cyclones. 6 of these went through the Gulf of Mexico, those being Hannah, Laura, Sally, Delta, Zeta, and Eta. The 7th one was Hurricane Isaias, which ended up affecting the east coast of the United States. In early 2021, this is where this quote comes from, Chairman Donnellan for Louisiana said that Laura, Delta, and Zeta combined cost the state $10 billion. But later in 2021, after the 2021 hurricane season also occurred, the Department of Insurance there ended up upping this, saying that Hurricane Laura actually cost the state as a whole $7.5 billion. And then Hurricane Ida, which was in 2021, cost the state $11 billion. And so the actual highest amount of losses were in residential property. And this is where it kind of relates to just the everyday average American. A lot of them were very, very negatively affected by this hurricane season. So now that we have an understanding of the force of the season, let's kind of shift our focus into an introduction of the diurnal cycle. The first part here is just kind of an overview of the scientific jargon that we're going to go over in the next the next 40-ish minutes. So we have Earth tells PV. I don't really have time to explain it, but we have the formula up here. We have the index that Hitchman and Shelley have created, which is what we call, and will be called further down the road, sigma PV, which is the root mean squared of potential vorticity variance over a given domain. And then also, throughout this presentation, I'll be talking about different domains that we looked at. I'll give a little bit more of an explanation on that later down the road, but we have a whole storm, which is our entire storm domain from the data that we get. We have a quadrant method, and we have an annulus method that will come up later. So, some of the earliest work that looked at tropical convection and its diurnal cycle is found in a paper by Gray and Jacobson in 1977. It wasn't focused on tropical cyclones, just convection overall. And so they had two different places where they looked at. One was a small island, one was a large island. In both cases, there's this peak in rainfall at about 6 a.m. local time, and then a minimum in the late evening, about 8 to like 9 p.m.-ish in the local time. However, when they looked at the large island and its diurnal cycle, they actually found two peaks. So they found the same morning peak, although it was a little bit smaller, and then they found an afternoon peak. And the reasoning for this that they give is that they thought it was due to a heat island effect. More recently, Jang et al. In 2011 used the Tropical Rainfall Measuring Mission Satellite, or TRMM for short, and they kind of narrowed it down to just tropical cyclones, and they looked at both convection and rainfall over ocean versus over land. And they had similar results. So here on the top is just overall general rainfall, and then on the bottom is heavy rainfall. And you can see in both cases that there is a pretty strong diurnal cycle, especially in this heavy rainfall. And they had the same timing. So there's a local peak at about 6 a.m. for both over ocean and over land. But over land, there was another peak later in the afternoon. You can see it about 6 o'clock p.m.-ish local time. To better kind of like visually see this, I just took one of their other plots. So this is still Jang et al.'s work. And here is their maximum that they found in between 4:30 and 7:30 local time in general rainfall, but also in heavy rainfall. And you can see here with the shading, which is due to precipitation rate, that there's higher reds here and a more area of the higher precipitation overall, but also just more area of the general precipitation too. And then for the most part, their minimum was in the 1630 to 1930 local time. And you can see a lot less area. There's still a little bit of that higher precipitation falling, but just a lot more condensed and not as much area overall. So the next paper that I looked at is Wu and Ruan's 2016 paper. And we're just going to briefly go over this and over one of the figures here. And we're going to look here at figure A, where they have brightness temperature plotted for both high clouds and low clouds. So high clouds is this black line, and how they indicated that was they used a threshold of 208 Kelvin. So anything below 208 Kelvin was considered a high cloud, and then anything between 208 and 240 Kelvin was what they considered a low cloud. The pattern that we see is that the high cloud aerial extent peaks right before sunrise, about 5 a.m. local time, but right after sunrise, there's a dramatic decrease in high cloud aerial extent. After noon, you start to see a low build back into that higher cloud aerial extent peak, which again peaks early morning the next day. There's actually an opposite pattern that we see in the lower clouds. So up until sunrise, lower cloud aerial extent is decreasing, but then after, in the afternoon, you have this high rise and a pretty long peak over the late morning, early afternoon, before it sunset starts to occur, and you're losing the solar radiation, and you have a high decrease again up until the next sunrise. So Rupert and Hoeninger used the isosahedral non-hydrostatic model to look at aggregation and diurnal cycle of tropical rainfall. They didn't look at tropical cyclones, they looked at organization basically. So they have two time periods. One is an unorganized time period, which is before 6 days in the model run. Then one is 55 days into the model run, which is organized. When they were looking at the diurnal cycle, they found a couple different results. The first one was that the organized diurnal cycle shifted earlier in the morning, closer to midnight, and then in the disorganized, it shifted to about 6 a.m. local time. The other aspect that they found was they tested Gray and Jacobson's theory of differential cloudy clear radiation effect, and they found that without a differential cloudy clear radiation effect, there would be a peak about 1900 local time, so that kind of pushes it back into the early morning. So the last paper that we're going to look at is a future paper from Professor Hitchman and Shelley Rowe, where they look at tropical cyclone Yasa in the Pacific. And we're going to just kind of break it down into two different things that I noticed is similar to the work that I've done that kind of helped me when I was first starting to check my work against theirs. So the first part is when tropical cyclone Yasa was category 1 or weaker classified. And we can see that there's a pretty pronounced diurnal cycle where we're peaking at about 6 a.m. local time in each of our peaks. Then we get to the later part of the storm, where now it's a mature hurricane, Cat 2 or greater, and these peaks have now ended up shifting to about midnight local time in each of the peaks and days during that. So that goes along with Rupert and Hoeninger a little bit. The lesser organized convection in the weaker tropical cyclone ended up peaking closer to midnight. The more organized convection ended up peaking at 6 a.m. for the lesser and midnight for the greater. So that leads us to our research questions, and I tried to make them broad and then have kind of subset questions that we'll go over throughout the duration of my actual talk, my research. So the first one is that kind of the general thought behind this is that we want to understand the dynamical adjustment process in high-resolution models of tropical cyclones. The actual question that comes from this, and this comes from a paper that we'll go over in a little bit, is potential vorticity a coherent variable when looking at the convective scale, specifically when we're looking at tropical cyclones? The sub-questions of how I'm going to get to this answer today are, the first one is, does sigma PV, our PV variance index, exhibit the morning peak and evening minimum seen in tropical cyclone convection and rainfall from literature? The second question is, does sigma PV propagate outwards like a pulsation, similar to the work done in Dunyan et al., where they looked at the cirrus canopy and a propagation outwards throughout the day? The last one is, does the diurnal cycle noticeably change when certain domains are over land? So with that, the next few slides are just going to kind of go over the procedures that I used for this work, and also to just kind of understand the subsetting that went in for each of the domains. So for this research, I used ECMWF IFS high-resolution data set provided through NCAR, and the data is every 6 hours. And so this has two good things, or a good thing and a bad thing. So the good thing is that there is very, very small spatial scale and for each of the grid points, which is great. It's high resolution. The kind of weaker part of it is it's every 6 hour, so we're kind of glazing over the hours in between each of the model data outputs. From this data set, we had a variable of interest, potential vorticity, and NCAR in their work transforms the original output into a Gaussian grid, which is really easy to use. There's also 26 vertical layers in the model, and we ended up using 100 hectopascal as our isobaric level that we used throughout my research. However, Shelley and Matt have looked at a bunch of different of the vertical levels and seen the same patterns that I've seen. So, why are we looking at potential vorticity? This comes from a paper, Liegenberg et al., where they were looking at 3,135 different convective cells, and they were tracking PV dipoles throughout it. And what they found is that they believe that PV is able to explain convective scale flow anomalies, and that we already know that it does well on both the synoptic and planetary scales, and it's beneficial if it does well on the convective scale, because then we have a variable that is really good at predicting all three scales, all three kind of sizes, which is beneficial in terms of just forecasting in general. And I like to think of it more as like a statistics linear regression model. You don't want to overfit. You want to use the variables that are going to give you the best fit overall, not the ones that you need the most to fit well. What they found is that the PV dipole strengthens with a stronger updraft. They found that the positive member of the PV dipole, which in my map of Hurricane Marco is the red, ended up being within the updraft, and then the negative member, which is the inertially unstable member, the blue in my map, is a little bit radially outwards. And so they also found that the PV dipole lasted even after the initial updraft had died, and this could actually influence secondary wave development in more convection. And so here I just had two plots. The first one is a satellite image of Hurricane Marco. The second one is just a potential vorticity plot, so nothing's been done to the PV. And there's one thing that I wanted to show. So this positive member here pretty much matches up really well with the center of the storm here. And then this negative dipole member, this negative filament from all the updrafts, ended up producing, you can see here, a lot of convection that goes outwards of this inertially unstable area, and not as much convection in the area where you don't have the inertially unstable member to kind of propagate convection. So, going back real quick to what is sigma PV, just so that it's a little bit easier to remember. So it's the root mean squared of variance of potential vorticity. Another way to think of it is just it's a spatial standard deviation of potential vorticity. That might be a little bit easier to remember overall. And then how we calculate it is it's over a certain domain. And so that goes back to our three domains that we showed before. First one being the whole storm, the second one being a quadrant method where you have 4 quadrants, the third one being an annulus method. So, what's the process of how we created this? After downloading the data from the ECMWF model, when we created our whole storm domain, we ended up having 86 by 86 grid points that we selected around the center of the storm. In the center of the storm, I determined using the National Hurricane Center's HURDAT data set, which is their best estimate of where the center is for every 6 hours. It worked out perfectly because well, I mean, it's still an estimate, but it works out perfectly in terms of timing because the timing of the HURDAT data and the timing of the ECMWF data. Sorry, no one wants me to update. All right, so the timing of the HURDAT data and the timing of the ECMWF data actually matched up each time period, which was great. Then, when we subsetted this down to a quadrant method, we had 43 by 43 grid points in each quadrant, and that's roughly about 3 by 3 degrees. And each quadrant is always labeled in terms of its axis point on a compass. So our quadrant 1 is always our northeast quadrant, quadrant 2 is always our northwest quadrant, quadrant 3 the southwest, quadrant 4 the southeast. Then we subset into an annulus method. And the reason for the annulus method, we'll still get to this a little bit later on, was I had read Dunyan et al.'s paper, and I had wanted to see if we saw any similarities between sigma PV and Dunyan et al.'s work on cirrus canopy. So in the annulus method, we ended up creating 3 different rings. The first ring is a ring of radius 1, that's what we call the inner ring. The middle ring is radius 2, and then you subtract the inner ring. And then the outer ring is radius 3, subtract the 2 inner rings. All right, so let's get into some original work, looking at a case study first of Hurricane Marco. As I said earlier, it was short-lived, but it was a Category 1 hurricane during 2020 in the Gulf of Mexico. It never made official landfall along the United States. However, the impact on coastal areas of the Gulf Coast and also Cuba and Honduras had some damaging effects. There was minor flooding in Cuba of about 5.7 inches was the local rainfall maximum. And then along the Gulf Coast, there were rainfall totals of about 3 to 5 inches overall. The first plot is a sea surface temperature plot with Marco's track being superimposed on it. And there's a couple different things that we can see here. The first thing is from our color bar, Cat 1 is our yellow color. There's only 2 time steps where it's a Cat 1 hurricane. So for the most part of Hurricane Marco's lifespan, it ended up being a tropical storm or tropical depression before it dissipated and after it formed along the coast of Honduras. The second thing is once Hurricane Marco tracks into the Gulf of Mexico, it is a very, very uniform sea surface temperature, which doesn't vary by more than 2 degrees Kelvin, 2 Kelvin. Then, the first plots that I'll show are time series plots of our entire storm domain and our sigma PV variability index. And so what we see first is we're focusing on how this lines up to literature. So in literature, when we looked at rainfall max and convection max, we saw that the peaks happened in the lesser organized convection later in the morning at about 6 to 7 a.m. And Hurricane Marco shows that pretty decently. So we have 2 peaks in our sigma PV variable at 7 a.m. local time on 2 different days. The third peak was shifted a little bit later back to 1 p.m. according to when our data was. However, again, this goes back to the 6-hourly data. This might not actually be peaking at 1 p.m. It might peak between 7 a.m. and 1 p.m. and be on a downward after that. We just don't have data to show that. More interestingly, the minimums that we saw fit literature really, really well. So this fits Gray and Jacobson and Jiang et al.'s work, where they saw that for the most part, the minimums in their rainfall data ended up being late afternoon, about like 7 to 9 p.m. And when we look at the minimums of our sigma PV index, we see that the minimums are about 7 p.m. on average, which is really good. The only day that wasn't was the day that it was still a tropical depression and really intensifying, and that could kind of lead to this difference in the minimum. Then, just to kind of show the diurnal cycle a little bit easier, I created a violin plot. And so what a violin plot does is it shows the density of where points are. And so obviously 4 days of data, 4 time bins, there's not much data yet. However, it still kind of represents an easy looking diurnal cycle. So here we see that there is a point in our 1 p.m. bin that is higher than everything else. However, there's only 1 point in the 1300 bin, and then the other 3 points end up being a little bit lower. So overall, if we look at densities of where the points are in our data, we see that there's a pretty pronounced diurnal cycle when just looking at density, with a peak at 7 a.m. and a pretty clear minimum at 7 p.m. Then, looking at our quadrant method, I did this just because I wanted to see if all quadrants are peaking in sync. In Hurricane Marco, they are, which is awesome. It doesn't happen in every case, so I'll just kind of throw that out there right now. So we see that overall, we have all of our quadrants peaking at 7 a.m. on the first day and the third day. 3 of them are peaking at 1 p.m. on the second day, with 1 kind of being a little bit earlier in the morning. Then the last subsetting that we did was to create the annulus method. And so the annulus method is going back to that inner, middle, and outer ring. And here, I was looking for any evidence of the variance of PV going outwards from the center of the storm during the diurnal cycle. And this relates to, finally, we're getting to Dunyan et al. So Dunyan et al. Created this clock figure where they were looking and tracking the cirrus clouds throughout the day of tropical cyclone, a couple tropical cyclones. And so here, they have a peak for their 100-kilometer ring, which is similar to my inner ring, at about midnight to 3 a.m. on average. The 200-kilometer ring peaked on average about 6 a.m., 300, 8 to 12 p.m. And then so on, they kept going out. I didn't. They had 400 in the early afternoon, 500 a little bit later, and then it all started to condense afterwards back to your 100-kilometer peak around midnight to 3. So let's go back to my work. Do we see this? Not really. So basically here we have our inner ring, which is our black line, and our middle ring, which is our green line, are peaking at the same time consistently. Then we have our outer ring, and our outer ring is peaking almost twice a day, once before every major peak in the other 2 rings, once after. So it's unclear. We don't really have any evidence of a propagation outwards when just looking at our case study. So with that, let's just kind of go over where we've gone and kind of an update on our research questions. So our first question was, does sigma PV exhibit the morning peak and evening minimum seen in tropical cyclone convection and rainfall? And similar to Gray and Jacobson's work, it does look like it does. Then, does sigma PV propagate outwards like a pulsation, similar to Dunyan et al.'s work? it's unclear. We're just going to kind of keep it at that for now. We can't really lean yes, probably leaning no. Last one is, does the diurnal cycle noticeably change when parts of storm are over land? This isn't looked at in this case study just because there's just way too few data to actually create knowledgeable input on the effects of land. And then lastly, I just want to put and kind of emphasize that there's definitely not enough data in just one case study to make these solid conclusions, and that's what kind of transitions us into our composite analysis. So I will show two different composites, but I'm going to go more in depth on the composite that has more data in it. So here is a list of each of our storms that goes into our composite data. If we kind of cut it off here at zeta, everything above it, that's in our 2020 composite, and then the whole thing is in our 2020 to 2022 composite. So we're going back to looking at the whole storm, and we're now breaking it up into more violent plots of different time periods. And so we have kind of our midnight time period, 6 a.m., noon, and then 6 p.m. Kind of how I'll label each of these later on. And what do we see when we look at this other than what looks like some nice Christmas ornaments that we can hang? There's a very, very weak diurnal cycle, maybe. There might not be overall. I see like maybe the density here is a little bit higher than that midnight, and this is a little bit lower than both of those, but there's nothing there that really pops out of the paper and says, hey, look, diurnal cycle. How about if I add the further 2 years for Cat 1 or weaker storms? Still nothing really. There's maybe a little bit more evidence of a 6 a.m. peak, and there's a little bit more evidence that these two are a little bit less than our early morning boxes, but overall, it's nothing that's like conclusively telling me that there's a pattern there when I look at it. Then, let's shift our focus to our mature hurricanes, which are Cat 2 or stronger. Clear cycle shown up now. There is a little bit less data, but overall, it does look like there's a clear peak in our midnight bin, and that goes down and progresses downwards to about our 6 p.m. When we add more data in, there's a little bit more effect on our mature hurricanes than our weaker hurricanes, and the reasoning for that is, again, just not having as much data. So this was actually more important to add the 2 further years for when we were doing statistical analysis on our mature hurricanes than it was for our weaker hurricanes, just because we needed the data to create better statistics. As we put in more data, the pattern pretty much stays the same. However, this here, our 6 p.m. bin, does look a little bit higher than our noontime bin in terms of just the distribution overall. But what I notice here is that this bin in our midnight bin has 2 different kind of peaks. One which is definitely higher in density and higher in value than your 6 a.m. peak, but one that's a little bit lower too. And then kind of moving on and just trying to visualize it a little bit better, I used a cat plot, which you can think of as just a double violin plot. And here I broke it out where the colors mean the weaker or the stronger storms. The stronger storm is in blue. Here we can see 2 things. The first thing is that in each of our bins, the data that we collected on mature hurricanes had higher sigma PV throughout every bin. The second is, or actually I guess there's 3 things. The second being that the diurnal cycle of our weaker storms in the orange don't seem to be that strong. However, the diurnal cycle is a little bit more prominent when we break it out with our cat plots. You can see that each of these have kind of this bimodal distribution, where there's just 2 peaks in our data. This one actually has 3 peaks, so trimodal. But if we just go off of kind of like density of points, it does look like that first peak kind of has a peak around midnight, and same with that second one is a little bit even to your 6 a.m., but then goes down from there. So we're seeing a pretty strong pattern still when looking at our mature hurricane pattern. So here's when I get into statistics, which is my love overall. The first test I did is an ANOVA test, which is analysis of variance test. And the results from this are a little bit similar to that of a t-test, where I'm testing the difference between means. However, now I can add in 2 or more groups. So basically, a significant p-value in an ANOVA test means that at least one of my groups has a different mean than my other groups overall. It doesn't tell me which one, doesn't tell me if it's higher or lower, just means that there's one that has a difference. When the first test I did was on our category 1 or weaker storms, and I'm testing the means of each of our 4 time bins. The p-value that I get is 0.468, not really significant on anything. So for the rest of this presentation, even though I've gone into results with the category 1 or weaker storms, we're just going to kind of take that out of the rest of the presentation for timing. The second test I did was on category 2 or stronger. And again, we're testing the means between each of the time bins. Our p-value is 0.001, which is very significant on basically every level. So the analysis for this is that I have at least one group, one time bin, which has a different mean than the other 3 bins overall. So to make this a little bit more palatable and less kind of wordy and harder to read, for each of the next few slides, I've kind of broken down each of my bins into a little bit of an emoji. So we have our midnight bin, which has a really nice moon. Our 6 a.m. bin is sunrise over the ocean. Noontime bin, even though it's not sunny in the hurricane, it's sunny in our noontime. And then sunset for our 6 p.m. bin. So, going back to our research question, the next slide that we go over is testing the assumption of the morning peak in mature hurricanes. So this is both going after Gray and Jacobson, Jiang et al.'s work, where there was a pronounced morning peak at 6 a.m. in their overall convection and rainfall. But also looking at Rupert and Hoenger's timing, where they had the more organized convection peaking closer to midnight. And that leads us to our next test, which is a one-tailed Welch's t-test. And why Welch's t-test? That's the first thing. So when using a student t-test, the assumption of a student t-test is that there is equal variance in each of your bins. I did a Levine test on my bins. Most of them did not have equal variance. Some did. And so that gets into our next talk. The Welch's t-test doesn't assume equal variance, but it doesn't say that it can't be equal variance. And overall, studies have shown that the Welch's t-test does really well in estimating a student t-test when there is an equal variance. So it's just a little bit safer to kind of use this over and over again than it would be for a student t-test and kind of gloss over the fact that there's not equal variance in all of my bins. And we got a little bit of our conquered grape jelly. So the time hypothesized greater is from literature, from Rupert and Hoenger's work, where when they looked at the more organized convection, it peaked closer to midnight. So we use our midnight bin for our hypothesized greater. For our hypothesized lesser, I throw in each of our other bins. And since this is a one-tailed Welch's test, I am able to say that I'm testing if the first one is greater than the second one, instead of the two-tailed test where I'm saying that the first one is different than the second one. So, when we go into the p-values and just statistical tests in general, the midnight bin has a higher mean than each of our other 3 bins. However, compared to the 6 a.m. bin, it's only a little bit higher. It's not statistically significant. Compared to our afternoon and evening bins, we see high significance. And also we see a lower p-value for this evening bin with the sunset. And that could mean, and it does mean, that it is slightly lower than our noontime bin's mean. So, answering our first question of morning peak. It does seem that the early morning peak is the greatest through our statistical tests. It's significantly greater than our noontime and 6 p.m. bin, slightly greater than our 6 a.m. bin. We also can infer through the p-test that our evening bin has a mean of slightly less than the mean in our noontime bin. And it does align with literature such as Jacobson and Gray, Jiang et al., and Rupert and Hoenger. Next question that we're going to go over. Testing the assumption that sigma PV propagates outwards similar to the pattern in cirrus clouds and Dunyan et al. So, a lot of numbers here. You don't really need to actually look at all of them. I've highlighted green means good, red means bad, but still kind of on that Christmas theme. Here, our hypothesized greater times are straight from Rupert and Hoenger's clock. So their inner ring, which was their 100-kilometer ring, peaked about midnight, or in that time period around midnight, so we hypothesized that that's great. Our middle ring, which is the 200-kilometer ring, in their work peaked at 6 a.m., so that's our hypothesized greater. the outer ring peaked at noontime, which is their 300-kilometer ring, so that for our outer ring is our hypothesized crater. We test that against each of our bins, our other 3 bins for each of our rings, and we find that in the inner ring, midnight is the highest peak. That goes with Dunyan et al.'s work. The middle ring, we're mainly focusing on this here, which is in red. The 6 a.m. bin is not a higher mean than the midnight bin. That goes against Dunyan et al.'s work. And then the outer ring, we're testing this noontime mainly against these 2 down here. And again, it is lower than both of those 2 means. So the mean in the noon bin is lower than our midnight bin and also our 6 a.m. bin. So analysis on this question. The sigma PV pattern does not propagate outwards at the same rate as cirrus canopy found in Dunyan et al. Is this bad? No. This kind of comes into like my background not being in weather. So they were looking at a cirrus canopy, whereas sigma PV and PV in general is looking at the updraft. And so the cirrus canopy overnight makes sense that the peaks would be the same because it's condensed down, but also you have your updraft right there. As the cirrus canopy spreads out, it's not an updraft problem, it's more of a solar radiation problem, which is creating that cirrus canopy to expand outwards. PV is not going to show that. PV is going to stick where the updrafts are, which creates our PV filaments that we saw in our PV graph, and therefore it really shouldn't actually follow from Dunyan et al.'s work. Doesn't make sense that PV does not have a similar pattern. I'm going to quickly show our quadrant method to see how it lines up to our whole storm data. So again, we're back to Rupert and Hoender's work where they said the midnight bin for your more organized convection should have the greatest rainfall and greatest convection. We go through here, and for the most part, it does look like that is correct. However, quadrant 3 looks really weird. And so that's when I kind of decided to dive into one thing which is a little bit different, but also a different analysis of this. And why is quadrant 3 acting differently than quadrants 1, 2, and 4? So that brings me to my last question of, does land affect the diurnal cycle of tropical cyclones? So this goes back to Jiang et al. And Greg Jacobson's work, where when a tropical cyclone was over land, you saw a little bit of a peak in the morning, but a greater peak in the afternoon in both convection and rainfall. When we're looking and breaking this down by quadrant, for the most part, we see this in quadrant 1. It might not be fully represented, but our red squares, which means that the quadrant is 10% to 25% overland, and our blue circles, which are 0 to 10% overland, we see a single peak that is overnight. And this is including both category 1 and weaker and category 2 and stronger. So that's why both the midnight bin and the 6 p.m. bin are pretty much equal. Our 25% to 50% shows actually that afternoon peak starting to occur. Our 50% to 75% doesn't show that. That could be difference in data, difference of dynamics, just a hurricane varying overall. But then we get to our 75 to 100% overland, and we do see that afternoon peak come back, and it's actually very strong. So that looks good overall. Quadrant 2, very similar. However, now our 25 to 50% is showing that overnight peak and not an afternoon peak, but our 50 to 75 and 75 to 100 shows an afternoon peak. We're going to skip over quadrant 3 because it's a little bit different. Go to quadrant 4. We see pretty much the same pattern kind of happening, so we're just going to kind of go from there. Then quadrant 3, our outlier for when we were doing statistics tests, still our outlier when we're looking at land sun. And so when quadrant 3 is over land versus when it's not over land, we are not seeing any change in the diurnal cycle. There's a weak diurnal cycle for each where you have a peak overnight, but no peaks in the middle when it's over land. Quickly, before we get into analysis on the land results, the first thing that I want to show is just when a storm is over land. So this is now the entire storm. And we see pretty much a pattern alluding that both are anything under 10% or under 25% over land shows that overnight peak with no afternoon peak. Anything above 25% shows an afternoon peak, except when we get to the whole storm being 75% or greater over land. I have two things of why this could be. The first one is that our bin for 75% or over, when we're looking at the entire domain, is very, very small. We don't have enough data there to really look and be like, this is conclusive that it doesn't. The second thing is when a storm, especially in the Gulf of Mexico, starts to make landfall, it starts to weaken very quick because it's losing moisture, and that could also be the reason why the 75% and over isn't showing that second peak. So analysis of this. Overall, when a domain is overland, it does look to alter the diurnal cycle, and overland and afternoon peak is found in sigma PV in most instances. What is going on in quadrant 3? And this is kind of, I was talking to Evan about this and I looked at it a little bit more. And so the reasoning that I've thought of is that for most storms in the Gulf of Mexico, you have your land up here and the storm is going normal to the land. So when we go back to how our quadrants line up, quadrants 1 and quadrants 2 are our northern quadrants, quadrants 3 and quadrants 4 are our southern quadrants. If a storm is becoming overland, then quadrants 1 and quadrants 2 are the first, if it's normal to it, that are going to be over dry air. So that dry air is going to circulate down into quadrant 3, and because it's drier air, it's not going to be conducive to convection. Then, as the winds start to pick up moisture from quadrant 3, which is at least partially overland probably, you're starting to see a little bit more convection in quadrant 1, in quadrant 4, and then quadrant 4, which is typically our lowest overland value, has a lot more convection going up into quadrant 1. So that's kind of just a dynamical approach to why we might be seeing a different diurnal cycle in quadrant 3. So with that, I just want to wrap it up with some conclusions and future work. The first conclusions are just going to look at each of my research questions and sub-questions individually. So the first question was, does sigma PV exhibit the morning peak and evening minimum seen in tropical cyclone convection and rainfall? And yes, it does look like that. We can conclude that yes, in our mature hurricanes from what we looked at, and even in the weaker hurricanes, when I did statistical analysis, it alluded to a 6 a.m. peak, even though it wasn't statistically significant. So to a lesser extent, in our weaker Category 1 or tropical storms or tropical depressions, there is still a slight diurnal cycle that appears. Next question, does sigma PV propagate outwards like a pulsation similar to a work done in Dunyan et al.? No, it does not propagate outwards similar to that, and that's because PV is found in the updraft and right around the updraft, and the propagation of the cirrus canopy does not have an updraft related to that. It's more of a solar process, solar heating. Last question is, does the diurnal cycle noticeably change when a certain domain is over land? And although there's no statistics shown, the patterns that we saw in all of our graphs does allude to that we see an afternoon peak start to form as a certain domain is over land. So our broader conclusion, going back to Wegenberg et al. With what we know from previous literature, potential vorticity does seem coherent in explaining convective scale flow anomalies, at least when we look at ECMWF model output. And then we kind of go into a little bit more of back to our first thing, similar to Rupert and Hollinger's work in weaker convection, there is a 6 a.m. peak that's a lot less noticeable, but in stronger convection, more organized convection, it shifts to midnight. Unlike Dunyan et al.'s work, sigma P does not pulsate outwards. And then the last one is the diurnal cycle over land does change in comparison to over ocean. So future directions for where our research group is heading. The next step would be, one of the next steps is to work on wind shear. Wind shear is very important in the lifespan of a tropical cyclone. And we want to see how that affects the diurnal cycle. And could it possibly be another explanation as why quadrant 3 is acting differently than our other 3 quadrants? The more important step is to add more storms to the composite. We're still a little bit low on data, and the next process for me will be to add the 2023 storms in. However, as of this presentation, the NHC has only published 7 of the 20 storms, and I want the HERDAT data to stay consistent with the data that I've used so far. Also, we want to add more basins. So Professor Hitchman and Shelley Rowe have looked at storms in the Pacific Ocean. I have looked at storms currently that have stayed out to sea in the Atlantic Ocean. But to fairly critique a diurnal cycle of tropical cyclones, we need more variety of these storms. It's not sufficient to say, hey, this happens in the Gulf of Mexico, therefore it happens everywhere. We want to have all of the basins kind of covered and into our process for using data overall. And with that, I just wanted to end with some thank yous. So thank you to Professor Hitchman and Shelley Rowe for helping me so much on this project. but also just in science in general. Committee members, John and Liz. Liz helped me a lot with coding the annulus method my first year here, so that was very helpful in the results overall. John has asked me many good questions in our GAC meeting that kind of made my mind process more, especially on that composite result. My mom and dad, because they probably heard so many rants from me about research. And then Cafe Social and Badgers Aquatics Club. So during my time here, I've worked a couple jobs outside of the department, those two being the two that I've worked. So Cafe Social, I was working there for the first year and a half. Badger Aquatics Club, very thankful to them, because it gives me 2 to 3 hours every day to get away from science, but also to focus on my love of swimming and being able to coach the next generation of swimmers. Lastly, all the friends that I've made at AOS, both in classes and in talking about research and just everyone in general. And then my kid in Smokey, I got him this past year. Been a lot of help mentally overall. So yeah, that's my presentation, so I'll open it up to questions. Yeah.
Why have you looked at storms prior to 2020? Does the data not go back before that?
So it goes to 2016, and my first inclination was to go forward, and that reasoning was Hurricane Ian. I was like really interested in Hurricane Ian as it started to hit Florida. So that was kind of my first inclination is, I'll go forward and I'll use 2021 and 2022. Our future work will also go back to 2016 though, with that ECMWF data. Yeah, Pete.
Question from Liz online. She says, apologize if I missed this. When you divided into quadrants, did you orient the quadrants by the storm movement direction or by compass direction?
By compass direction, yeah. Yeah, John.
Yeah, Dan, very interesting and seems promising. I don't quite understand how the sigma PV is a proxy for the diurnal cycle of convection. Can you explain that to me?
Yeah, so we have an updraft from the hurricane, and that updraft creates a diurnal filament dipole. And so each of the updrafts causes a separate PV dipole. The positive dipole being near the center of the updraft, the negative being a little bit radially outwards of the updraft. And you can see as the updraft grows, and this is with Wegenberg et al. Too, that PV dipole becomes even stronger and stronger. So that would be kind of like a little bit of convection in there, but it's kind of looking at also just updraft strength.
Does that depend, so that confirms what I had floating around in my head. I think I maybe have heard this before in other talks too. But does that depend on what the original tropopause structure is? What if you have a tilted tropopause already and you have some of your strong updrafts hitting it at a higher spot than some in another storm that hit it at a lower spot? Is that going to change the variance of your PV and your relatively small domain, 3 degrees by 3 degrees?
I think that overall it might have minor effects, but I think that goes into Hitchman and Shelley's work a little bit, where, yeah, I only focused on the 100 hectopascal, but they've looked at the entire UTLS in general, and they have seen a similar pattern at each of the levels. So I think that even with tilting, that it would be a similar yet like slightly different pattern.
It would still stand out as the most intense anomaly.
Yeah, and so that gets into
it seems like in the Atlantic, the tropopause climatologically is pretty close to 100 hectopascals, so this works. It would work with relative vorticity too.
Because the stability is so high when you get
But in the Pacific,
exactly.
the Western Pacific, sometimes 70 hectopascals is a bigger signal.
Yeah.
And so it does
I
drift
can
between
go-
those recorded, archived levels.
And so I think when in part of your future work, that would have to be maybe the first level characterization of different basins, right? What's the average tropopause level height?
Absolutely.
Definitely.
And then you can't proceed until you do that, but that's easy to do.
Definitely.
Okay.
And so this was kind of like, you explained it a little bit about the static stability, but just the increase in static stability from 150 to about 100 to 70 is like 25 times.
Yeah.
And so that goes into part of that,
Yeah, okay.
It's a mundane explanation for this shockingly large signal. It's just there's a step function increase of PV relative to relative vorticity at the tropopause.
If I could ask a follow-up based on this?
Yeah.
Because this was in my mind too as I'm listening to your interesting talk. Is there any advantage to thinking about just the vorticity at 100 millivolts?
Yes.
Possible, yeah.
Yes.
And they've looked at mean of PV so far. But yeah, vorticity too, probably.
Yeah, because it seems like it's a more straightforward inversion people can do in their heads about what that means for circulation and so on.
No, now that you say that, it is a bit of a red herring. People get very excited about PV, but if we just set this all in terms of relative vorticity, there would be as concerned.
Yeah, that's right. And yet, it's easier to digest and understand, perhaps.
Somehow,
Yeah.
we all like PV.
Yeah.
It still is a little bit mystery.
Okay, thanks. Very
Yeah,
interesting.
for sure. Thank you. Yeah.
Liz just had a follow-up, and she said it might be worth considering orienting by storm movement so that the quadrants are more similar across all the different storms.
Definitely, yeah, that was something that I think came up when Professor Hitchman last presented last year. But also that, and I know that Nuo had mentioned basing the quadrants off of wind shear too. So yeah, definitely something in the future that can be worked out.
But, well, I mean, the whole storm does is diurnal pulse, so
Yeah.
that's not, the shear's not going to change. Any other questions or comments? Well, let's thank God again for a very nice work.